It begins not with a cataclysmic boom or a blinding flash of light, but with a silent, imperceptible drift. Imagine waking up one morning, the world outside your window looking exactly as it did the day before. The sun rises, traffic hums, and the rhythms of daily life proceed completely uninterrupted. Yet, high above, an astronomical event of profound significance has just occurred without any fanfare. The moon, our constant celestial companion, has quietly and inexplicably shifted its orbit. It has not vanished, nor has it been struck by some rogue asteroid. It has simply backed away, settling into a new, stable orbit that is precisely 10% farther from Earth than it was yesterday. 10% farther. 38,440 kilometers. This change, a mere 38,440 kilometers, sounds almost trivial in the vastness of space. This seemingly minor adjustment in our cosmic neighborhood presents a fascinating hypothetical scenario. It's a change so subtle that no one on Earth would immediately notice. There would be no breaking news alerts, no panicked calls from observatories, and no immediate visual difference in the night sky to the casual observer. The moon would appear only marginally smaller, a detail even avid stargazers might initially miss. Instead, it invites us to explore the intricate, delicate, and often overlooked connections that bind our planet to its natural satellite. It is a journey into the cascading consequences of a single, simple alteration to a fundamental constant of our world. What if the moon suddenly moved 10% farther away? The answer unfolds not in minutes or hours, but over days, months, and years, as the planet slowly responds to this fundamental change in its gravitational relationship. This is a story of quiet, cascading effects that ripple through Earth's systems, from the deep oceans to the delicate balance of coastal ecosystems, and from the schedules of global shipping to the generation of renewable energy. For millennia, the moon has been a source of wonder, a muse for poets, a guide for navigators, a deity for ancient cultures. But beyond its cultural significance, the moon serves a critical, practical function: Earth's gravitational anchor. Its pull is the primary driver of the ocean tides, the rhythmic rise and fall of sea level that has shaped coastlines and governed marine life for eons. A 10% increase in the moon's orbital distance would result in a nearly 17% reduction in its gravitational pull on our planet. This is the trigger for our entire chain reaction. The very first and most profound consequence would show up in the oceans. The rhythmic pulse of the tides would immediately begin to weaken. A tide that once rose 16 meters might now only rise about 11 meters. Tidal currents would slacken. They shape sandbars, scour shipping channels, and create complex sediment transport patterns. The very sound of the coast would change. Gentler, less energetic. The intertidal zone, that vibrant and dynamic region exposed at low tide and submerged at high tide, would shrink. For the countless organisms specifically adapted to the cycle of wetting and drying, this would be a catastrophic event. The impact would extend beyond the rocky shores into the world's most productive coastal wetlands, salt marshes, and mangrove forests, which act as critical nurseries for commercial fish stocks and protect coasts from erosion, are exquisitely sensitive to tidal inundation. The result would be a slow-motion collapse of these vital ecosystems, setting off a new cascade of environmental and economic problems. The immediate consequences of diminished tides would ripple through the arteries of global commerce with surprising speed. Ships would be forced to wait longer at anchor outside ports, burning fuel and incurring massive costs. Cargo would be delayed. Ports would have to scramble to implement emergency dredging, costly and environmentally disruptive. The economic impact would be immediate: billions in lost revenue, higher shipping costs, and supply disruptions. Beyond shipping, renewable energy would also be hit. Tidal power generation would be crippled. Existing tidal barrages and lagoons would operate far below design capacity, economically unviable overnight. Finally, coastal community safety would be subtly but significantly compromised. Protective ecosystems, salt marshes, and mangroves would be degrading. During a storm, surge would hit a less protected coastline, increasing severe and unpredictable flooding. The moon's retreat would also subtly alter the very rhythm of time itself. The synodic month, new moon to new moon, stretches to over 34 days. Cultures and religions that use true lunar or lunisolar calendars would be hit immediately. At the same time, tidal breaking, Earth's rotation slowing from tidal friction, changes. The rate our day lengthens would slow. Minute, but it impacts systems that keep global time. GPS satellites, financial market transactions, and telecommunications networks must be recalibrated. The collapse of salt marsh and mangrove nurseries would lead to a precipitous decline in catches. Coastal communities built around fishing would see their livelihoods vanishing almost overnight. Aquaculture operations that rely on tidal flows to deliver food and remove waste would also suffer. The degradation of protective wetlands would expose real estate and infrastructure, triggering a collapse in property values in many seaside locations. Over decades, a more subtle impact would manifest. The energy from tides is a crucial ingredient in driving the vertical mixing of ocean water. With tidal forces reduced, the oceans would become more stratified, with less interaction between them. The transport of heat towards the poles would slow down, potentially leading to regional cooling in areas like northern Europe and fueling more intense hurricanes in the tropics. A more stratified ocean would also slow down its absorption of CO2, potentially accelerating the rate of global warming over the long term. In the face of these disruptions, humanity would be forced into a massive engineering and technological adaptation effort. Coastal defense would move away from hard engineering toward dynamic, nature-based solutions. The collapse of traditional fishing economies would trigger significant social upheaval, leading to mass migrations. This shared challenge could, paradoxically, bring humanity closer together, forcing a global perspective on problems that transcend national borders. In the end, the Earth would not be destroyed. After the initial chaos, our world would settle into a new, stable, but permanently altered state. The most enduring change would be the diminished tides, high tides, forever lower, low tides, forever higher. This is the new baseline. A quieter coastal reality. The Earth-Moon system. Weaker gravity, still stable under new parameters. The world would be fundamentally, yet manageably different. Life and civilization adjusted to the shallower breadth of the ocean and the more distant gaze of our celestial companion, finding stability in a quieter equilibrium. Ultimately, the scenario of a more distant moon serves as a profound thought experiment in dependency. It forces us to see the moon not as a passive ornament, but as an active and critical component of Earth's life support machinery. The real challenges were not meteors or tidal waves, but the mundane yet critical failures of logistics, economics, and ecological services. The moon, now slightly smaller and dimmer in our sky, would serve as a constant, silent reminder of our place in the cosmos, not as masters of our domain, but as inhabitants of a complex system. What scenario should we explore next? Share your ideas below. You've been watching IfVerse, where imagination meets possibility. See you in our next reality.